They haven't had one group that's had another one. They just announced they're doing all their classes virtual for the first like 3 weeks. Oh, yeah. No, February.
Like something can't come.
I don't think so.
Yeah, it looks like the number of cases is doubling on campus now every 2 days. So up to 20 cases on campus now. So. Us, yeah, let's see, last Wednesday it was 5, and then it was 11 Friday, and it's 20 today. So it's, we're in this exponential growth phase.
Are they actual confirmed cases or people just with like symptoms that may be the flu?
These are supposed to be tested. Confirmed cases. That's not even, that doesn't count for people who are quarantined. So.
Did you know even if you have the antibody test and if like you test positive for antibodies, you still will have to be quarantined if you come in contact with someone?
That's UE policy or?
Because I asked you that question. I was like, what if I go get a test and it's negative and I go get an antibody test and I do have the antibodies, can I come back? They're like, no. You have to have 7 other tests and then I'll even consider it and we'll talk to the CDC for you. Like, well, that's not. I would.
So start taking, if you've gotten lax in your precautions and mask wearing, and I have noticed some students in the building not wearing masks, make sure you wear your mask all the time in the building.
They expect us to pay for it. They gave me like 500 tests that I would have to take for them to even talk to the CDC. But letting me come back early, I was like, I guess I'll just wait my 14 days. I got home.
You did it.
I wasn't even sick. That was awful. You're like, if you were sick, that might be one thing. I was like, so you got to be sick. Then not. Okay.
I think I know what to do. Everything else except for. And which is just good stuff. Yeah. What you need to test? I don't know. Some the one where it's like complex one. Because that's a big real concept. And then I look at the book, it wasn't making sense. That's fine. Okay, who did it? I don't know. I started from there. And I was like, that's not right. Yeah, I didn't think it was so bad. Please say anything else. It's not even.
Okay, so I want to talk about Fourier transforms today, and the definition. We'll look at some examples. I want to talk a little bit about negative frequency that means. We've kind of been using it at this point, but really haven't talked about it. The Fourier transform allows us to extend our frequency analysis to non-periodic signals. So up until this point, we've been looking at periodic signals with Fourier series. The definitions of the Fourier transform. So Again, uppercase letter to represent the transform of a time domain signal. And it's defined in terms of an integral. It's x of t e to the minus j omega t et. So it looks similar to the Laplace transform, but substituting j omega for s. The inverse transform, so with the Laplace transform, that was a contour integral in the complex plane. For Fourier transforms, it's a standard integral. S of omega e to the j omega t d omega. So this is Fourier transform and the inverse Fourier transform. And again, Fourier transforms are typically used in filter design, communication theory. Laplace transforms tend to be used more in control systems, study of stability. Fourier transform also can be implemented. There's a version of it, the discrete Fourier transform, that can be implemented in computer software. And so that's actually the topic of the course next semester, the DSP course. The other notation you'll see here is, and similar to what we have used for the Laplace transform, x of t, and it's a double-headed arrow to get x of omega. So x of omega generally will be this e to the minus j omega t is a complex signal, right? We can write it in terms of use Euler's formula. It's cosine minus omega t plus j sine minus omega t, but it's a complex function of time. So x of omega will typically be a complex function of the real variable omega. It's complex because of the presence of j there. Unlike the Laplace transform, it's a complex function of a complex variable. So the Fourier transform is a complex function of a real variable omega. It does have real and imaginary parts for magnitude and phase. We often work with those. There are a few, at least today, there are a couple of instances where we'll calculate the inverse transform using this integral definition. But like the Laplace transform, once we build up a small table of transform, we will rely on the table for finding transforms as well as finding inverse transforms. And then the other thing to note here, some differences between the Fourier transform and the Laplace transform, is that the integrals over all time with the Fourier transform, whereas Laplace transform units just from t equals 0 to infinity. So that means that, I guess depending on how you look at it, the Fourier transform automatically includes initial conditions because it goes all the way back to minus infinity. Or you can look at it another way and say, well, it doesn't allow you to include initial conditions like the Laplace transform. They're actually built in, but the transform itself goes all the way back to negative infinity. So a couple of common Fourier transform pairs. We want to build up this table. So you start by trying to find the Fourier transforms of some of the simplest signals that you can think of. We don't really like maybe the impulse because it's this abstract thing, infinitesimal width and infinite amplitude, but it does really behave really nicely under an integral. And so from the definition, minus infinity to infinity, delta t minus t0, e to the minus j omega t dt. If you remember, what this does is really just sample this function at t0. Okay, good. So the product here, we can apply the product rule for impulse. It'll be delta t minus t0 e to the minus j omega evaluated at t0, but that then becomes a constant. and then the interval of the impulses is 1. So this becomes e to the minus j omega t0. So it is a complex function. X of omega here is a complex function. It's a function of omega. T0 here is a constant. Okay, so here's our first Fourier transform pair. Now, as a special case, what's the Fourier transform of delta t? Just 1, right? Because that's equivalent with t0 equal to 0, but e to the 0 is 1. So simple special case is the Fourier transform of an impulse. So we want to start thinking about, in the frequency domain, that tells us when we look at the content in the frequency domain, it tells us what frequencies make up the signal. This says that for an impulse, it's a constant 1 in the frequency domain. It consists of all frequencies equally from minus infinity to infinity. Again, it's not a real signal. We can't generate it. Going back to the general case, here x of omega is e to the minus j omega t0. Of course, we can write that as cosine omega t0 minus j sine omega t0. In Euler's formula, this expands as cosine of minus omega t0, but cosine of a minus is the same as cosine of omega t0. And then it would be, plus j sine of minus omega t0, but sine's an odd function. So we can pull the minus sign out like that. So this is a complex function of omega. We're used to thinking of these trigonometric functions as being functions of time. But t0 here is a particular delay of our impulse. So these are functions of omega. What's the magnitude of x of omega? Square root of the sum of the squares, right, of the real part and the imaginary part. So square root of cosine squared plus sine squared is equal to 1 for all values of omega. So the magnitude is equal to 1. The angle, and this is easy if you think about, e to the minus j omega t0 as being a point on the unit circle, right, at an angle of minus omega t0. But it has a magnitude or a length of 1, and then the angle would be, we could get it as, it's the inverse tangent of the imaginary part over the real part, but the inverse tangent of sine over cosine is the inverse tangent of the tangent. So the angle is just becomes minus omega t0. But that's just, you can see that actually more readily in the from the exponential form. So what we do a lot of is plot the spectrum, plot the Fourier transform. Now, because it's a complex function, how do you plot it? You could plot the real and imaginary parts. I could plot the cosine in one plot and the sine in the other. But the magnitude and phase give us a lot more information about what frequencies are contained in the signal. That's actually in the magnitude portion here. Well, it's easy to plot the magnitude spectrum for this particular signal, right? It's a constant 1. This would be, and this would be called the magnitude spectrum. So if we talk about the Fourier transform of a signal, like a time domain function, an x of t. We can talk about the spectrum of the signal. We'll also be talking about the frequency response, which will turn out to be the Fourier transform of the impulse response. But that the frequency response, we use that term when we're talking about circuits or systems, and use the term spectrum when we're talking about signals. Now the phase angle, it's not too difficult to plot. So x of omega is just minus omega t0. So minus omega t0 would just look like this, right? A straight line with a slope of minus t0. M equals minus t0. But by convention, we just plot this when it gets, and it might be shown in radians. I'm going to plot it here in degrees. At some point, we're going to get to minus 180 degrees. By convention, when that wraps around and we jump up to plus 180, it will look like this. And similarly, we get back to 180 here. We jump down to minus 180. By convention, the phase angle is always shown between plus or minus 180 degrees. So you can plot these pretty easily in Octave, and you'll see the discontinuities in the plot like this. They're jumps. They're not really discontinuities. It's just that the phase is wrapped around. You get the minus 181 degrees. That's the same as positive 179 degrees. Well, let's actually now, since the impulse is so easy to integrate, and we've got just a regular integral here in the inverse Fourier transform, let's talk about this thing. What is an impulse in the frequency domain? So this would be an impulse in the frequency domain at omega 0. So this would be a plot of delta omega minus omega 0. Well, we can plug into our inverse Fourier transform now. Delta omega minus omega 0. Notice that these, the Fourier transform, the inverse Fourier transform, are pretty similar. And you've got a minus sign here. There is no minus sign here. There's a 1 over 2 pi here. If you actually write this in terms of f, the 2 pi goes away because d omega is 2 pi df. The 2 pi just cancels out. So if you write it in terms of the frequency variable hertz, it looks even more similar. But here again, now we're thinking about this as a function of omega. So this becomes just 1 over 2 pi e to the j omega 0 t. So we could write this as 1 over 2 pi e to the j omega 0 transformed into delta omega minus omega 0. It's written in our table in the book like this. Multiply both sides by 2 pi. Delta omega minus omega 0. Okay. So e to the j omega 0 t transforms into 2 pi delta omega minus omega 0. So it transforms into this, in the frequency domain, it shows up as an impulse just at the frequency omega 0. Similarly, e to the minus j omega 0 t would transform into 2 pi times delta omega plus omega 0. That's an impulse at omega equal to minus omega 0. So this starts to give us a clue about a meaning of negative frequencies for complex signals. And people can argue about what's the meaning of a negative frequency for real signals. because cosine of minus omega of negative 0 t is the same as cosine omega 0 t, right? But for complex signals, we do have to take into account this negative frequency and what that means. So if you think about this time domain signal, e to the j omega 0 t, it has a, write this as cosine omega 0 t plus j sine omega 0 t. So it has a length of 1 for all t. So we can think of this as a point on the unit circle, and then the angle it makes is omega 0 t. Okay. That's how we can kind of visualize what this thing does, what this looks like in the time domain. So this is the real axis, this is the imaginary axis. So it's really this point that's spinning around on this unit circle as time increases. Right. With t equal to 0, we have e to the j omega 0 t, or 1. With omega 0 t equal to pi over 2, so t would be pi over 2 divided by omega 0, then e to the j pi over 2 is j. When t increases, so it's the points here, it's minus 1, and then j, and then all points in between, okay, that have a magnitude of 1. But it's this point that's spinning around on the unit circle. It has a real part that's cosine omega 0 t, and it has an imaginary part that is sine omega 0 t. Okay, just from basic trig. So we can think of that again, that's where Euler's formula comes from. This e to the j omega 0 t. So this thing is spinning this way. Has a real part along this axis that can vary between positive and negative, and has an imaginary part along that axis. Now, so what would a negative frequency signal be? Well, it would be one that's actually just going in the opposite direction at an angle of minus omega 0 t. So it would be, our omega 0 t, we can think of as this point that's moving counterclockwise around the circle. Minus omega 0 t is this point that's moving clockwise around the circle. And this is this visualization for this complex signal. Now notice what's going to happen, though, if I add these 2 points together. I'm going to double the real part, right? They have the same real part, but they have equal but opposite imaginary parts, right? You see that? And when I add this point that's going in my positive frequency direction to this point that's going in my negative frequency direction, plus e to the minus j omega 0 t. What I'm going to get is 2 cosine omega 0 t. Right? This real signal, the imaginary part goes away. We cancel because this is plus j omega 0 t. This would be plus this is plus j sine omega 0 t. This would be plus j sine of minus omega 0 t, or minus j sine omega 0 t, and the imaginary parts would cancel out. But this is nothing more than a form of Euler's formula, right? Divide that by 2 on both sides, and I've got another form of Euler's formula. So I can get a real signal by adding together 2 complex signals. One that one that's rotating in this counterclockwise direction, a positive frequency component with a negative frequency component that has the same amplitude or length, but is rotating in the opposite direction. So if I add this positive frequency component and this negative frequency component, I'll get a real signal. We'll see that the Fourier transforms of this is a complex signal. Right? It resulted in this impulse here at omega equal to omega 0. We'll see that for all the real signals that we'll work with, that there'll be a certain symmetry in the Fourier transform domain. will have both positive frequency and negative frequency components that have a certain symmetry. That's required so that when we add them together, we get a real signal. So we'll talk more about that. We'll talk more about that symmetry. Certainly for this case, that you can see that symmetry is present. Here in the first example, we had a real signal. It's not complex, but we have this symmetry in both the magnitude spectra, it's even, and in the phase spectra, it is odd. Okay. Next, couple other signals we need Fourier transforms for. Be nice to see cosine omega 0 t. What's the Fourier transform of that? Well, the easiest way to do that is just write this using Euler's formula as this, and we've already got the Fourier transform of those. So 1/2 e to the j omega 0 t is going to become pi delta omega minus omega 0, and then we'll have plus pi delta omega plus omega 0. Okay, so to get this cosine, we really need two impulses in the frequency domain. Its positive frequency component of this exponential plus its negative frequency component. So that the two, when they're added together, give me the real signal. So similarly, we can do sine omega 0 t is pi over j delta omega minus omega 0 minus delta omega plus omega 0. Or the other way that you can write this, if I multiply numerator and denominator by j, I'll get, in the denominator I'll get a -1, but in the numerator I'll get pi j. And I'll get a minus sign here that I have to distribute. I can put a minus sign there and a plus there. It's usually written as delta omega plus omega 0 minus delta omega minus omega 0 though. But cosines and sines become impulses in the frequency domain. They consist of just single frequencies. And we'd say the frequency is omega 0, even though we've got this negative frequency component. Now, another very common signal is this pulse signal. And we use the notation RECT, or rect, to represent it. This is especially important in digital communications. Now, the denominator there is the total pulse width, tau. So that means it goes between minus tau over 2 and plus tau over 2. And this has a height of 1. By definition, I just multiply it by 10 to make it a pulse that's 10 volts high, or what if we're using voltage. It's relatively easy to find the Fourier transform of this. Just from the definition, it's minus infinity to infinity of rect t over tau e to the minus j omega t dt. But the rect function is 0 outside, for all t less than minus tau over 2, and all t greater than tau over 2. And inside that interval, it's just 1, e to the minus j omega t dt. So we can do this integral, it would be minus 1 over j omega, e to the minus j omega t, evaluated at minus tau over 2, plus tau over 2. And we get, I'm going to move the minus sign inside the brackets here. I'll get e to the j omega tau over 2. That's at the lower limit, but I swap these terms. Does this look familiar at all? E to the j theta plus e to the j theta should always remind you of, I had cosine written down here somewhere. E to the j theta plus e to the j theta, e to the minus j theta should always remind you of cosine. E to the j theta minus e to the minus j theta should always remind you of sine. So this is actually 2j sine of the argument, but then I'm dividing by j. So I'll get here 2 over omega sine omega tau over 2. Let me continue up here. For x of omega, I'm going to do a little trick and write this as it's the same. Yeah, that would just be 2 over omega. And the taus will cancel out. I'm trying to get in the form of sine theta over theta, okay, or sine x over x. And it is equivalent to the previous line. Just take the reciprocal of the denominator, and taus will cancel out. But this sine x over x is another standard form, or it's a form that appears a lot in the study of Fourier transforms. It's called the sinc, but S-I-N-C instead of S-I-N-K. It's called the sinc function. And did you see this in circuits? Remember seeing this in circuits? May have looked at it earlier in this course as well. Now, what's kind of interesting, again, this is a function of the symmetry of x of t. When x of t has even symmetry, x of omega will be entirely real. In general, x of omega will be this complex function. But if x of t has even symmetry, x of omega will be entirely real. If x of t has odd symmetry, x of omega will be entirely imaginary. It will just be a j term that we can factor out. In general, it is a complex function. But here's an easy, kind of a nice one to work with, because in the Fourier transform, we end up with a function that's entirely real. So let's talk a little bit about the properties of the sinc function, sine x over x. Now you have to be a little careful. Some books will define sine pi x over pi x as sinc of x. I think MATLAB may do that. So the MATLAB definition may be a little bit different than the definition that we typically use when we're working with Fourier transforms. But a couple of what's sinc of 0? If you let sine 0 over 0, what is it?
Sine of 0 is 0.
Sine of 0, 0. So what's sine 0 over 0? It's one of those indeterminate forms, right? So what do you have to use to,
Limits.
huh?
Limits.
You have to use limits, but there's a one for finding that limit of 0 over 0. L'Hopital's rule. Okay. Take the derivative of the numerator, divide by the derivative of the denominator. The derivative of the numerator, derivative of sine is cosine. The derivative of the denominator, sine x over x, is just 1. So it's the same as the limit as cosine of beta with beta going to 0. So it actually, it is, you can try that on your calculator. Put it in radian mode. Take the sine of a small angle and divide by the small angle. Another approximation that you commonly run into is for small x, sine of x is approximately equal to x. So for small x, dealing with the limit here as x goes to 0, this is equal to 1. And then the other thing is for we know sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0. So sinc of n pi is 0 because of that. And it's not when n is equal to 0 because that's when we get the indeterminate form. But for all other values of n, we've got sine of pi over pi, which is not indeterminate, that's 0. Sine of 2 pi over 2 pi, again, that's 0. It's only at when n is equal to 0 that we get that indeterminate form, and instead of getting 0, we get 1. So this is kind of enough information for you to draw a rough sketch of the sinc of x function as a function of x. We know at 0 it's equal to 1. When x is equal to 1, I think this is my notation here. Yeah, when actually, so when x is equal to in this notation when it's pi, and then 2 pi, and 3 pi. And then also for minus pi and minus 2 pi. Now, these are 0 crossings, so it actually does something like this. It's sine, but it's oscillating. As we get larger and x, the sine x over x, our denominator gets larger, so the ratio gets smaller. So this thing is an oscillating sine, but it's decreasing in amplitude, okay, as x gets larger. It does have even symmetry. Sine x is odd, but x is odd also. The ratio of two odd functions is even, as is the product. So it's only because this thing, so this should be, it looks something like that. So you'll see this shape over and over again in signal processing, antenna theory, digital signal processing, image processing. So what we have is rect of T over tau. Fourier transform becomes tau sinc omega tau over 2. So where we would solve for this particular function, we want to solve for the values of omega, where omega t tau over 2 are equal to n pi. That's when we know we're going to have the 0 crossings. That's going to be at frequencies of omega that are n times 2 pi over tau. So now if I want to draw the magnitude of this function, it's real. So if I just draw the magnitude, it's really just taking the absolute value of it. So it looks very much like the same function. So now my zero crossings are going to be at 2 pi over tau, and then 2 times 2 pi over tau, and 3 times 2 pi over tau. Minus 2 pi over tau. 2 times 2 pi over tau. Okay. And then at 0, it's actually equal to tau, because it's multiplied by tau there. So we'll talk more about this, but you talk about the frequency content of a signal. Well, this thing really contains all frequencies, right? It's getting smaller and smaller, but we can say that the frequency content of the signal is concentrated between, when you talk about the frequency content of the signal, the convention is just to use the positive frequencies. Okay, that's all we normally talk about. We can say that the frequency content is mainly between 0 and 2 pi over tau for this signal in omega. Or in hertz, it would be between 0 and 1 over tau. Now, what that means is, what's going to happen to this thing, to our zero crossing here, as our pulse gets smaller and smaller. As tau gets smaller, 1 over tau gets larger, right? So as our pulse gets narrower and narrower, this thing becomes broader and broader. So just kind of in this rough sense at this point, narrow pulses have greater frequency content, consist of more frequencies than wider pulses. The extreme case of that is that impulse over there. When we get to an impulse, it consists of all frequencies. We've got a 1 all the way across. This is what the magnitude response would look like of this real function. What's the phase response look like? This is a little interesting, because here it's entirely real. Right? What's the phase angle of a real number on the real axis? It's just 0. Right? So it's 0 here. Well, what's the phase angle of a negative number? 180 degrees, right? Or minus 180. Either way. So that's in this next interval. So I'll just show it as minus 180. You could actually show it as positive 180. So here it would be, it's negative, it's positive here, and we'll jump down to minus 180. So the idea is that we would be able to reconstruct the frequency content from the magnitude phase response. So it's just in this particular function, it's entirely real, so I can just plot it, and there's actually all the information is contained in this real plot. But in general, we can't do that. And I'm going to plot the magnitude phase. And typically, this phase angle is shown as an odd function, so it's often depicted like this. But plus 180 is actually the same as minus 180. It's shown with odd symmetry. Okay, let me just give you, I'll just list a couple of others, and then we'll call it a day. The derivations for some of these are in the book. The signum function is one that you don't run into very often. It's used primarily because it allows us to get the Fourier transform of the unit step. But the signum function is just the sign of its argument. So if the argument is positive, the signum function is +1. If the argument is negative, the signum function is -1. It's also called the sign function. Okay, it just gives you the sign of the argument. Signum of +10 is 1. Signum of +100 is 1. Signum of -2000 is -1. Okay, if the argument is negative, it returns a -1. If the argument is positive, it returns a +1. So, but if you think about it as a time domain function, you know, it looks like this. Calculate the Fourier transform of this. I'm not going to go through the steps. It's 2 over j omega, or again, you could write this as -j 2 over omega. The magnitude response is just 2 over omega, right? It's entirely imaginary. And the phase response is, well, here, as long as omega is positive, angle's -j, right? So it's -90 degrees for omega greater than 0. If omega is negative, then this becomes +j. But I'm not going to draw those. But we can write the unit step as 1/2 signum of t plus 1, or 1/2 signum of t plus 1/2. And I think I didn't go back and look at this one special case here, which I need this now. If omega 0 is 0, I do get 1, a constant 1 transforms as just 2 pi delta omega, right? I guess I erased it, but I had, you know, delta t transforming as 1. But in the frequency domain, a delta in the frequency domain comes back as a constant, 1 over 2 pi. I need that so I can find the Fourier transform of this. But if you do that, we've got the Fourier transform of the signum function. This becomes pi delta omega plus 1 over j omega as the Fourier transform of a unit step. Now, normally we think about it, an impulse at the origin at omega equals 0 as that's a DC component. Now, a big difference with the Fourier transform versus the Laplace transform, we can talk about Fourier transforms of signals that only exist in negative time now. Fourier transforms over all time, right? So we wouldn't even talk about the Laplace transform of this because it exists only for t less than 0. But x of omega of this signal becomes pi delta omega minus 1 over j omega. And you can write this in terms of the signum function as well. It's 1/2 minus 1/2 the signum function. And then finally, we know how important the exponential function is. And we can write this now as an exponential for negative time. But the Fourier transform of this is 1 over a plus j omega. Fourier transform of e to the minus at u of t is 1 over a plus j omega. If you remember, the Laplace transform of e to the minus at u of t was 1 over a plus s, or 1 over s plus a. So here it's the same except j omega instead of s. Now this is a complex function. Of course, the magnitude is just going to be 1 over the square root of the sum of the squares. What's that going to look like? Omega equals 0, it's going to be 1 over a. And then as omega increases, the denominator gets larger, so it's going to look something like this. It's going to be the magnitude response for that. The phase response, I'm not going to draw it, but it would be the phase angle of the numerator, which is 0, minus the arc tangent of the imaginary part over the real part, omega over A. All right, I think that's enough to get you started with some basic transforms. We'll continue this next time, start looking at some inverse transforms and some circuit analysis. And these problems are a lot easier than the Fourier series problems. Fourier series problems are a pain. I know that. There's integrals, infinite summations. But these are much easier.